Hello class. So today we start off from where we left during Tuesday's lecture. Just a sec, I don't know why is this. Okay. So last class we saw methods to determine how roughness factor and how it affects your head loss, volume flow rate, and what diameter should be designed such that all these different parameters are taken into consideration. We saw primarily that the analytical form still for turbulent flows we can use for head losses, which is pressure drop or HL. This is pretty much due to viscous effects, right? And you have to find out the friction factor, length, diameter, velocity from individually if you are asked to do so in a class, and then you have to use a solver using typically a MATLAB solver or Wolfram Alpha or whatever package you're familiar with. The other way is using these three sets of equations, what we call it as the empirical form, basically given by Swami Jain. They were probably advisor. Swami is probably the advisor and Jain is the student. Correct me if I'm wrong, but that's why they are known as the Swami Jain formulas. They are empirical, meaning that there is plus minus 10 to 15% of error involved. If you were to use the simultaneous equation form, then you have to rely on Colebrook equation, Moody chart, Reynolds number. Essentially you start off from this fundamental equation and then you go down, determining each term. Okay, so today we will start with minor losses. And what are minor losses and how is it different from major losses? So major loss is essentially what we saw, HL or delta P, which is due to viscous losses through a straight pipe. Okay. Minor losses are losses which happen in a pipe network because of disruption in flow, primarily owing to design of the pipe. So for instance, bends, tees, valves, inlets, outlets, expansions, these causes disruption in flow and which gives rise to minor losses. And so typically you would have in a piping network losses which are major due to pressure drop because of due to the viscosity effect, and because of the obstruction, because of a valve or a bend, which is the minor losses. So it is a sum total. The sum total is major loss plus the minor loss. Okay, so for minor losses we have something known as the loss coefficient KL, and again this will be provided to you in a typical chemical engineering plant in the form of appendix, like a sheet, or depending on what material is being used, what type of obstruction is to be encountered, and these coefficients are usually typically provided. However, it's important to know what is the form of expression for this minor losses? That is the loss coefficient. So KL is the loss coefficient, which is head loss here due to a minor, and again delta PL is minor here, and so this HL minor it is additional head loss due to presence of component. So to find KL, we measure delta P in pipe with and without the component, and here we consider the same total length of the pipe, and the difference is whatever difference you find is due to this is with the component, without the component. When you measure delta P, the difference is the loss due to presence of an obstruction, in this case a valve. Okay, so minor losses are important when sizing pumps, etc. To account for the effect, again the total head loss is the major head loss due to viscous effects, pressure drop, and the minor, and it is always a summation. And note that this is additive. These losses are additive, and they are additive when diameter and velocity are constant throughout. Okay, a less common way to account for the pressure drop delta P is we find equivalent length. So equivalent length concept can be seen here. What if there were no obstruction? What would be the equivalent length of this pipe without the obstruction, which will account for this loss? Okay, so that is another way to look at it. So L equivalent is diameter divided by the friction factor times KL, the coefficient. Okay, and head loss by a component is the head loss caused by a section of pipe with length L equivalent. So that is another way to look at it. Okay. All right. So now, if you are in a lab, or when you'll be doing the unit ops lab, one of the things which will be very important is knowing KL for different types of bends. So you have sharp edged here KL, and this is a well-rounded bend, and as you can see, sharp edged worse than smooth. So these are some of the design considerations. You want to smooth out the bends in order to minimize the loss coefficient. And again, these are approximate only. You should consult the manufacturer handbook for details. The other thing is, what is to be kept in mind is, even though you have a bend, the pipe exit also introduces losses. This is like a pipe inlet, which is part of a cross section of the pipe, but in the exit, there is always a consideration based on the kinetic energy. So the loss coefficient is typically a kinetic energy correction factor, which is the kinetic energy correction is alpha equal to 2 for fully developed flow and alpha equal to 1.05 for fully developed turbulent flow. And the thing to note is that for exit considerations, shape of outlet does not matter, because fluid enters a larger body at the outlet and comes to a stop. So essentially it's like the pitot tube problem, where you have a complete conversion of kinetic energy. And so total energy loss is the kinetic energy correction factor. So total energy loss is the kinetic energy correction factor. Okay, so now let's look at the scenario where, so I'll get stuck. Where you have you're dealing with not inlet and outlet, but expansions and contractions in the cross section of a flow. Okay, so as you can see here, sudden expansion, you have of course the kinetic friction factor, but you have to modulate it with the diameters. The D is the small diameter, and the small d is the diameter of the smaller pipe, and the capital D is the diameter of the bigger pipe. And so this is just a theoretical basis for expansion. Sudden contraction, on the other hand, if you are, it's the reverse. If it's going from a larger diameter to a smaller diameter, there is no real theoretical basis. And what you use is essentially an empirical chart. And so basically you can see here, sudden change in losses is way greater than the gradual change in losses. And similarly, the gradual expansion and contraction based on velocity, this is something you should always remember, d by d value. And these are really design considerations. I was hoping to give you a tour of the Unitops lab to see in live action how you can apply these equations. I don't know, I don't think under these circumstances this will be possible. But anyway, so the bends and tees, this is another important thing. As you can see, if it is you typically want always smooth bends versus edged bends. And again, you have to, these are design considerations to be checked with manufacturer handbook. Valves, very important. This is something you will be using routinely in laboratories if you're going to do graduate study, or if those of you will be joining industry, this is extremely important. Why have different valve values? Because depending on the application, so you can have on-off valve versus gradual control of flow. Check valve to prevent from going blunt, etc. So this is very important, and you'll be probably doing exercises with these values in your Unitops lab. Okay, so now let's look at a quick problem, multiple choice question. Water flows through a narrowing pipe and a straight pipe of equal length. The energy of the fluid flowing through a narrow pipe dash compared to flow through a straight pipe because of what? So A increases because of the continuity equation, which by our intuition no. B decreases, the energy of the fluid flow through a narrowing pipe decreases compared to flow through a straight pipe because of frictional forces. So most likely this is the answer. Decreases because of Bernoulli's equation stays the same, because so these are not correct. Okay. For a given piping system, the major losses will be higher than the minor losses. True or false, or depends. C. D depends on the turbulent or laminar flow. So this really depends on how long your piping length is versus the number of components. So it is always a tug of war on the length of the pipe, which really is the viscous forces are dependent on the length of the pipe versus the number of components. So it really depends. Okay. Water flows steadily through a smooth pipe that has 6 elbows in it, and the head loss due to the elbows is delta PA. The pipe is then remodeled so that the number of elbows is reduced to 4. What is the relationship between the pressure drop after remodeling, which is delta PB, to delta PA for the same flow rate? Okay, so essentially you have delta PA, you have 6 elbows, and now it is remodeled to 4 elbows. and this is directly proportional to delta PA over delta PB. So therefore delta PB is equal to 2 by 3 delta PA. And why am I using this relationship? Because losses are additive. So essentially, so that means your answer is this. Okay, so now it's good time to go into piping network, which is again a reality of most chemical engineering plants, because rarely you will find straightforward piping structures. Most of the piping structures you will find are in either series or parallel. And so in this particular situation, pipes in series, what do you have? Your volumetric flow rate at A is equal to volumetric flow rate at B, and which means that HL total, the head loss total, is essentially a summation of the HL at individual piping unit. So HLI, I here is A, B, C, depending on how many segments of changes you have. Okay, so it's a summation. Now let's look at pipes in parallel. So pipes in parallel, you have flow coming in and it is branched to two different piping sections. So here your incoming flow V total, the volumetric flow rate, is isokinetically split. Isokinetically meaning the kinetic energy is conserved, and this is something. So your volumetric flow rate is so essentially you have, so I here is again 1, 2, 3, so on and so forth. The thing to remember is head loss is same in each branch. So HL1, head loss in first branch, is equal to head loss here. HL2, which implies, if you write down the equation, L1 D1 times V1 square over 2G is equal to F2 L2 divided by D2 V2 square over 2G V1 over V2 is F2 over F1 L2 over L1 D2 over D1 is the square root of that. And what is the volumetric flow rate? V1 over V2 cross-sectional area of 1 times velocity which is equal to D1 square over D2 square F2 over F1 L2 over L1 d1 over d2. Actually, sorry, this should be d1 over d2. Because it's in the denominator. d1 over d2, and this is again the square root. Okay, so this is the expression for volumetry from the V1 and V2. Now, there are two rules for piping networks. First one, as I said, it's isokinetic split, so conservation of mass is must hold. The other thing is delta P HL between the two junctions must be same for all paths between the two junctions. Again, by isokinetic, meaning that the kinetic energy is isometrically split. So that is what I mean, just one way I look at it. But for the scope of this class, I don't want to go into it. Just remember this concept. And so this junction concept, as you can see, should remind you of your high school level physics, or freshman physics class, electromagnetics, where we looked at Kirchhoff's law of current flow, right? Circuit laws. So this is a common way to look at it, and so this law also here applies for fluid mechanics as well. Here, analogy is, instead of current, your flow rate is current, pressure drop, and analogous to electrical potential. You can sum up all loops, and the sum, as Kirchhoff's law dictates, delta P, when you sum it up, because of the sign convention, delta P equal to 0. So you let HL greater than 0 for, this is a sign convention for clockwise direction, less than 0 for counterclockwise direction. Very important. So when you are looping it, remember that your sum of all the loops, the pressure drop should be equal to 0 because of this sign convention. Very important. Okay, so now that we have figured out the basics of piping networks, what are the types of piping networks, and what are the losses that can be encountered due to viscous effects and due to obstructions in the pipe, let's come to the pump, the choice of pump power, and with the knowledge of head loss, how to choose the pump requirements. That is a very important concept, because in the end of the day, what is the good of a head? What is the usefulness of determining head loss? Head loss means that this is essentially the extra amount of work which need to be done by an external system to ensure that the flow reaches from the entrance to the exit point, right? So once you have a piping network, you must know what pump to use, or vice versa. How do we go about it? your head loss will eventually be needed to be plugged into the energy equation. Remember this from your chapter 5, Bernoulli's, where we had the pump added to the left hand side, turbine extracts, so it's on the right hand side, plus head losses. So this is what is providing the power, this is what is generating it. Okay, here alpha 1 and alpha 2 are kinetic energy correction factors. Depending on the flow. So go back to the kinetic energy correction factor. I'm just going through it quickly, but this is where, so for a fully developed flow, your alpha is equal to 2. For turbulent flow, it's equal to 1.05. This is the kinetic energy factor. Okay, so and HL is total losses. Major plus minor. Once you calculate the total losses, you can eventually get an estimate of the effective head, right? Head required. So effective head is always in length, right? Meters. And you can find the actual energy requirement. So for the pump shaft system, this is the equation what the pump has to provide, and this is the electrical output for a pump motor system. All right, so this is what I meant by this is a pictorial depiction of the concept, just what I explained, the useful head. So when a pump moves a fluid from one reservoir to another, in this particular case, you see there is the only difference here is there is a height imbalance, right? So reservoir 1 is at a lower height, reservoir 2 is a higher height. So your head, useful head, pump head requirement is equal to the elevation difference between the two reservoirs. So this is the extra amount of energy which is needed to be provided by the pump such that the fluid reaches from its starting point to the end point. And this is what exactly the role of a pump is. Okay, and this is essentially the efficiency of the pump motor combination. It's the product of the pump and the motor efficiencies, which is where this term comes in. So this is what is a pictorial output. Unfortunately, we'll probably not have the opportunity to look at the cross section of a pump and what really produces it, things in live action for this particular class, but if you just get the hang of it. Now let's look at the scenario where you calculate, this is the scenario, you calculate the head loss in a piping network, the total head loss. How do you choose the pump characteristics for your network. This is where you have to rely on something known as the pump performance curve. So this is very important, so I just want to take some time to describe. So our goal is to determine if you choose a pump randomly, how the pump will interact with the piping system. So a random choice of a pump, if you just go to your Home Depot or any other store and buy a pump system, you will have to find out how the pump will interact with the piping system and is it the right pump you purchased. So where do we start? First is, when you purchase a pump, you will be provided by the manufacturer with something known as the head versus flow rate chart. Okay, your H pump, head loss of the pump and the efficiency of the pump curves as a function of flow rates. This is the red. So your H pump, so the efficiency of the pump curve as a function of flow rate is the red perforated line. This is provided by manufacturer, and so also is the head of the pump. So head of the pump is essentially when the pump exit is close to produce the maximum head, meaning that the exit is pretty much blocked close to the piping system, and here it is the free delivery where no pipe is attached to the pump. So essentially there is no load at all. So this is where the pump is tightly bound to the piping system, and this is where there is no real no pipe is attached to the pump. So this is the curve which you will be provided. Okay, so what do you do? First is you need to calculate for your piping network your system curve. System curve is your total head loss of your network versus volumetric flow rate. So this is the system curve, blue system. So in green perforated line, this is your system curve, and what this system curve is telling you, this is how much head requirement is for your piping network. Okay, now once you do that, now you plot your system curve on top of your H pump U and efficiency pump curves which are provided by the manufacturer. So essentially you plot your system curve on top of your efficiency curve and your H pump, the head loss curve. So this is essentially your poor efficiency. Anything this is your best efficiency point. Or BEP. Okay. Now, where your system curve intersects pump head, that should be your operating point. So here your system curve is intersecting your H pump curve. This is your operating point. And this is your supply curve. So this is the point where you should be operating your pump ideally. The other thing to check after you have done this is check if by operating it at this point you are getting sufficient flow rate and or you are getting the desired efficiency. So to recap, choice of pump: first, after you calculate your head loss, you plot your head loss, your total head, the system head, in meters as a function of flow rate, volumetric flow rate in a piping system. This, you will get a curve like this, which is known as the system curve. This system curve, you overlay it on top of your manufacturer provided efficiency, the pump efficiency and the head loss of the pump efficiency and the head loss of the pump curve. The point at which a system curve intersects with your H pump, the head of the pump curve, that should be your operating point, and you should always operate it beyond this point such that there is, your supply curve, meaning this is where your system should be supplied the power. Okay, so now we look at a problem. This is an example from your book, pumping with parallel pipes. Water is being pumped as shown. Pipes made of commercial steel, so you have your roughness height as this. Motor pump combination is 70% efficient and draws 8 kilowatts of power. All minor losses are considered to be negligible. What is the total flow rate and the flow rate through each of the pipes? That is what is being asked. So you really have to first determine what strategy to use to solve this problem, so they don't spend too much of time to just plug in the numbers, etc. So that's the first thing. Understand the concept. So you have you are given rho, volumetric flow rate, GH, pump U, right, the head of the pump, and the efficiency of the pump motor. So you are given the power, electrical power, and the equation for this is this, and these are again H pump U and N pump motor are manufacturer determined. As we have seen, from the pump performance curve. So what you have, 8000 watts is equal to density 8 kilogram per meter cube times flow rate times 9G value H pump U, and the efficiency is 0.7. So this is what is given. So now you have to use your energy balance equation, because you're dealing with a piping structure here. So always whenever you have to deal with a piping network, your energy balance is your go-to equation. Okay, so EA rho G plus alpha A velocity A square over 2G plus height CA plus your head of the pump. Okay, so this is equal to PB rho G plus alpha B height ZB plus head loss. Now VA, this is almost equal to 0, large reservoir, right? We are looking at PA and PB goes to 0, atmospheric pressure. So your H pump U is equal to the elevation difference ZB minus ZB plus HL. The height difference is 8 meters. Plus HL, and what is HL? HL, because it is a parallel piping, your losses through 1 is equal to losses through 2. Okay, so now let's find out HL. What is HL11? F1 L1D1 V1 square over 2G is equal to F1 length is L1 36 meters, diameter is 0.04 meters times V1 square over 2 times 9.81. Again you repeat that for HL2, and what else do you have? V1, right? What is V1? Velocity 1 is volumetric flow rate divided by cross-sectional area pi d1 square over 4 is equal to volumetric flow rate divided by pi 0.04 square by 4. How do you calculate F1? Using the Colebrook equation, the friction factor is equal to minus 2.0 log. You are given a material epsilon or the roughness height. So that should give you a hint that at some point you'll be using the Colebrook equation, plus 2.51 RU1 square root of F1. What is the Reynolds number? 1 rho V1 D1 equal to mu. So this exact same, this line of this whole set of equations to solve for HL1, you repeat for HL2 too. Repeat. The other constraint you have is the volumetric flow rate. Total volumetric flow rate is V1 plus V2. So now you solve equations simultaneously. All the equations simultaneously to get V total 0.03 meter cube per second. And volumetric flow rate through the piping network of 2 is 0.0259 meter cube per second. And so this is what you find. Also, the interesting thing is the diameter in pipe 1 is half of diameter in pipe 2. But so look at the split in the volumetric flow rate. V1 is only 0.14 times V2. So this is an interesting factor. So this is how you solve such problems. You start off with your electric power equation, then go down. It's like a top-down approach. Pump, always start with the power equation where you have the efficiency and everything else. Then you will go down to energy equation to find out the missing term in that equation. So always a top-down approach. You start off with the major equation, the missing term, the governing equation is energy balance here to find out H pump U. When you have an expression for H pump U, the head of the pump, you will find that you need the knowledge of head loss. That's where your piping equations come in, and for head loss you need this equation, which the friction factor and everything else, and then this is the simultaneous set of equations which you need to solve simultaneously. Okay, so let's look at another problem, which is gravity driven flow in pipe. So water at 10 degrees Celsius and 998. Yeah, I think this should be 997, but that's okay. Okay, and you have the viscosity term and flows from a large reservoir to a small reservoir as shown here. This pipe is cast iron, roughness height given. Determine the elevation Z1 for the flow rate of 6 liters per second. Okay, so here in this problem there is no pump, nothing. It is just the simple gravity driven flow. So top down approach again, there is no pump, so you have to deal with the energy equation. Energy balance. So you have P1 divided by G alpha 1 P1 square over 2G Again, this is equal to 0 at the top of the reservoir at 1 plus Z1 rho G. This goes to 0 plus alpha 2 V2 square over 2G. This goes to 0 plus Z2 plus HL. Okay, so this gives you what? Z1 is equal to Z2 plus HL. What is HL? HL is HL major plus HL minor losses, which is equal to F L over D plus summation of the minor loss coefficient times V square over 2G. Okay. What is V now? Volumetric flow rate divided by pi d square over 4, which is in this 0.006 meter cube per second divided by 0.05 square over 4, 3.06 meter per second. Your Reynolds number is rho VD over mu, which is 117,000, and the knowledge of, you have to, even because you're given this roughness height, when that implies that you have to use your Colebrook's equation, 0.0052. So if you use this in Colebrook's, you get an approximate F of 0.0315. So there, now plug all these values into your HL equation, which is this. This is the form. Right, so this is what you get. Zero 0.0315 times 89 meter per 0.05. 3 plus 0.3 plus 0.2 plus 1.06. So at the exit KL, it is 0.2. You have two elbows, 0.3, 0.3. Okay, and this F goes in here. Okay, so times .06 square divided by 29.81. So velocity square divided by 2g, which is equal to 27.9 meter, which gives you, now you know Z1, you know HL, you can calculate now Z1. Here, right? So this is Z2 equal, this was the expression we got from the energy balance, so plug that in. Z1 is 4 meter plus 27.9 meter, which is 31.9 meter. So this is your answer. Okay, so then now the final subsection of this chapter is flow rate and velocity measurement. You have already seen parts of it in chapter 5 using the pitot tube and all. We'll just briefly go through it, especially when you have obstructions and change in the diameter of the pipe, sudden contraction, sudden expansion. So what are the different devices to use? These are really difficult to sort of give you the importance of it in a theoretical manner. Here it should be really done in a hands-on fashion to get a feel for it. So lots of ways to do it. So the most classical way is a pitot tube. As you see, you kind of stop the kinetic energy and you have a stagnation point, and from where you can find out the velocity, the stopping velocity, right? So we have all seen it. What is the advantages of it? Very little interruption, to the flow. Such a small device, really, something like this. It looks even smaller when you will actually see it in live action. The other thing is that it is really simple, cheap, and surprisingly very reliable based on first principle calculations. The disadvantages is you must be careful. When positioning it in a pipe, so when positioning it in a pipe, because you could be encountering try not to encounter a turbulent region when you put it. Okay. You also have obstruction flow meters, venturi, nozzle meters. So these are typically used as well. And the equation to use for these is very similar to what you learned in the chapter 5. Essentially, it's a mass balance equation for the obstruction too. The only thing here is when you have contraction or an inlet or an exit, that you have to modulate your equations from chapter 5 with a d over d, which is the diameter of the small pipe versus the larger diameter. So that's pretty much it. And this is essentially what we call it as the correction factor. This is modulating the equations what you learned with the correction factor, which is d over b. There is also another correction factor to be used. So this is one problem, example 810 in your book. Just go through it. I don't want to solve it. It's pretty straightforward. Is a discharge coefficient. So discharge coefficient is an addition to your beta term. And what is it? This discharge coefficient, it corrects for extra non-ideal losses caused by obstruction. And this is again, this term is provided by manufacturer, and it depends on again your beta, that is your ratio of small d over capital D, and your Reynolds number, as you can see, because this non-ideality increases with increasing Reynolds number. And so this is something to remember. So essentially you are modulating your fundamental equations for orifices, venturi and nozzle meters from your chapter 5 with the beta term and your discharge coefficient. So this is essentially what the practical use of these equations are. Other types of meters which you will see is positive displacement meter, turbine meter, and things. Now you have ultrasonic flow meters where you can, this is what we use in our lab, where you're actually trying to measure how much sound, the change in the sound wave from the flow of a fluid in a pipe. That will tell you how much velocity is, what is the velocity of the fluid. So there are, of course, these things are more advanced topics and also needs to be investigated in more of an advanced class. So there is also a variable rotometer where the displacement of the spring is proportional to the velocity of the fluid, which in terms is the volumetric flow rate, which is proportional to that. So these are some of the more advanced types of meters to find out, to characterize the volumetric flow rate and velocity and so on and so forth. So this sort of finishes chapter 8. We really looked at, the contrasting governing equations for laminar and turbulent flow. Really, there is no real governing equations for turbulent flow. That's why I use empirical equations. Laminar flow, we saw that it is a parabolic form and how to apply it correctly. Determine the flow regime from Reynolds number and calculate the entry length. In the turbulent flows, we saw the most important thing is the friction factor, which is used to calculate pressure drops in pipe using the equations. We already went through it in solving problems. Losses, then you have depending on the roughness of the pipe, how do you calculate the friction factor using the Colebrook's equation, and then also the flow regime. So if it's a very high flow, the Reynolds number is going to change. Do you use a Moody chart? So there is minor losses and how they affect pump pipe requirements, and there are also major losses. So these are the different types of losses we saw. We also looked at, after you calculate all the losses, everything in a piping system, how do you choose a pump? This is where the pump performance curve is important. Particular pump, again, you have to draw your system curve, overlay it on the manufacturer curve, and then intersection is the operational point. Then finally, briefly, we touched about how to measure flow rate, pitot tubes, and also there are more fancier versions, but the driving equations are very similar to the ones we saw in chapter 5 using Bernoulli's. The only difference is that we are modulating it with a discharge coefficient and a correction factor, which takes into account of the different diameters of the pipe. So that's pretty much it. I hope you spend sufficient time in this chapter. This is really important also for you going forward in the future. So this is, as I said, the most important class, most important chapter with respect to the knowledge you will be using in the future. Thank you.